Hi AP Calc students, this is a complete review of the entire year. It's going to include both Calc AB and Calc BC, but the BC only topics I'll make sure to, notify you that it's BC only. So AB students can just skip that part of the video. So I'm going to go through the entirety of the content, all 10 units of content, and I'll go over some example problems or procedures along the way just to help reinforce the concepts. So let's get started with Unit 1, Limits and Continuity. So this one's the very first unit, small part of the course as a whole, but it's very foundational to the course. So what is a limit? A limit is basically the value that a function approaches as it approaches another value. So limit as x approaches a of f of x is equal to L is an example of a limit. As x approaches a, the value of the function f of x approaches the value of L. So if I have a simple example like in the function x squared, as x approaches 2 on both sides, f of x approaches 4, because just 2 squared is 4. So graphically, you can do it that way. If you have a table of values, you can just converge on the point you're looking for, in this case 2, from both sides. And if you have an equation, I'll get to that in a second, some of the times you can just plug in a value into the equation, but if that doesn't work, there are some other techniques that I'll talk about in a little bit. So this is a limit. There are a few basic properties of limits that you should know that do help with plugging stuff in algebraically. So the limit as x approaches a of the sum or difference of two functions is just equal to L plus m. So in this case, L is the limit of f of x, m is the limit of g of x, and plus or minus, because I also included differences in this. So yeah, when you're given an addition or subtraction of two functions, you just add or subtract their corresponding limits. If you're given a coefficient in front of a function, so like a multiple, a constant that you multiply to a function is just equal to the constant times the limit. Just simple properties that are common to most functions. When we get a quotient, as you might expect, it's L over m, except for one scenario where m is equal to 0. So you have to make sure that m is not equal to 0. If m is not 0, then you can divide them fine. And then when you take the composition of two functions, so if it's g of f of x is just equal to g of the limit of x approaches of a to f of x. So that looks a bit weird, but you can just, that would just become g of L. All right. Yeah. Moving on to from properties of limits to one-sided limits. So here, all we've been talking about were two-sided limits, where you have to go from both sides. One-sided limits are just one side. So you have limit as x approaches a of f of x. If you kind of tweak that to a minus, that means it's going to be coming in from the left. So this would be a minus from the left. And then a plus would be from the right. So those are just the one-sided limits. And we say that the limit itself exists if and only if both one-sided limits exist and are equal to each other. If limit as x approaches a minus of f of x is equal to limit of x approaches a plus of f of x. So both of these have to exist on their own, and they both have to be equal to each other. Only then does this limit exist. Two special limits that you should know how to evaluate, going back to kind of the properties of limits. When you go to 0 of the function sine of x over x, you can't really just use this, because m would be 0 in this case, when limit of x approaches 0 of x equals 0. And so you just have to know that this is equal to 1. We'll learn a few tools later on in this year or in this video that will help you prove it or derive it. But for now, you just have to memorize it. Similarly, 1 minus cosine of x over x is the same story, except this would be equal to 0 instead of 1. All right. What about infinity? So you can have limit as x approaches a of f of x, quote unquote, equals infinity. A lot of times you don't want to write equals infinity because some people think that nothing can ever equal infinity, which makes sense. So instead you would write d and e, but approaches infinity, which is much longer, and it's just simpler to write equals infinity, but that's not technically correct. So if this happens, then you have what's called a vertical asymptote, which I'm sure you've learned in like pre-calc before, where you have a function like this that has a vertical asymptote. That basically means that the function is not defined for that value, and it goes to infinity one side, negative infinity the other side, or it could actually just go like this, where it goes to infinity both sides. So this is usually going to be a one-sided limit that goes to infinity. You can also take the limit of something as x approaches infinity, and that gives you what's called a horizontal asymptote. Basically, if this value exists, and it's something like 0 or 2 or 5/4 or something, that means that it has a horizontal asymptote at y equals that value. So yeah, that's that. Another thing is called the squeeze theorem. The squeeze theorem is a theorem that basically states if you have a function that lies between the graphs of two other functions, and the two other functions have the same limit at a certain point, then the function between them also has the same limit. Basically saying, I have these two functions like this, and I have another function between them. We don't know what happens in the middle, but since it's between them, it has to go through that exact same point, which basically means all three of them have the same limit. It's useful in some cases when you get some weird complex functions, but you're almost never going to use it on the AP exam. Okay, getting to the second part of this unit, which is continuity. Continuity is basically checking whether you can draw a graph without lifting your pencil up. That's like the informal definition of continuity. We've got a formal definition, which is just three criteria that a function must meet. First of all, if a function is said to be continuous at a certain point C, or a, it doesn't matter the variable, f of a must exist. If the function itself doesn't exist at that point, then it's not going to be continuous. You have to take your hand off to draw it. The limit as x approaches a of f of x must exist, and that goes back to this criteria right there, which basically says that the one-sided limits should exist and equal each other. And then the third thing is that f of a has to be equal to limit x approaches a of f of x. That's basically making sure that it's not like a jump somewhere. And I'm actually going to get into the three types of discontinuities now. The first one is a jump discontinuity, where you have a function like this, and then you have a hole in the function and the actual value of the function somewhere else. So in this case, the limit would be this upper point here, because that's where the function is approaching as you look at the nearby values, but the actual value of the function is down here. And so number 3 would be violated. Then we got, this is called a removable discontinuity. A jump discontinuity is similar, except for the fact that the entire graph changes. So the entire graph kind of jumps one place. And so this is going to violate number 2, where the limit of the function exists. And then the last kind of discontinuity is an asymptote, which we've already kind of talked about. And that's going to violate condition 1, because the function doesn't actually exist at a vertical asymptote. There are groups of functions that we know are always going to be continuous at every point in their domains. So we've got polynomial functions, rational functions, power functions, exponential functions, logarithmic, and trigonometric. But you might be thinking, well, rational functions, those are the ones with asymptotes. How are they going to be always continuous? They're always continuous for every value in their domain. This value doesn't even appear in their domain, which is why they're not continuous at that point. So if a function is continuous, then you can just plug it in to calculate the limit. That's how you can calculate algebraic limits. And then the last part of this unit is called the intermediate value theorem. It's another theorem, often abbreviated IVT, basically saying if f of x is on an interval a comma b, it's continuous on that interval. And if there's a value d such that f of a is less than d is less than f of b, or vice versa, it could be f of b is less than d, which is less than f of a, that means there's at least one number c such that a is less than c is less than b. such that f of c equals d. That was a lot, but basically what it's saying is you got a function, f of a is here, f of b is here. That means that the function must cross every point between f of a and f of b at least once, because it's continuous. You can't just, go here and then disappear off here. If it's not continuous, then that works. But we specify it has to be continuous on that entire domain, and so it has to go through all the points. You cannot draw it any other way. So yeah, that's limits and continuity, pretty basic. I'm not really going to go over any example problems on this because they're relatively simple and you should know them to actually study calculus. So yeah, that was the first unit. Moving on to derivatives. So we finally get into like the bulk of calculus. It's differentiation, properties, and definition properties. So this one is where we actually get introduced into what a derivative is and like the formal definition of a derivative. We're also going to be talking about the derivatives of some common functions. It's a relatively short unit, so I don't expect it to be too long. All right. So what is a derivative? So a derivative is the rate of change of a function. It's the instantaneous rate of change of the function. The average rate of change we should know is from x equals a to x equals b is f of b minus f of a over b minus a. That's just the formula for rate of change or slope or whatever. Now, if you change b into x equals a plus h, that means it becomes f of a plus h minus f of a over h, because a plus h minus a is h. Now, if you take the limit of this as h approaches 0, you're going to get the instantaneous rate of change, because that's basically saying, this is a plus h. We're just bringing a plus h closer and closer to a. So instead of being a secant line that goes through both points, it's just going to be a tangent line that goes through exactly one point. And that's what the derivative is. It gives us the slope of that tangent line. So that's the formal definition of a derivative. You can also write it as f prime of x or y prime or dy dx. All of those are just equal to that limit over there. We have to make sure that the function is differentiable at a point A. Basically, the conditions for that is it must be continuous at point A, the function. And the second condition is that if you take this limit and the one-sided limits of them, they have to equal each other. So limit h approaches 0 negative, it should be equal to limit h approaches 0 positive. That's not correct notation. You have to actually write what's in the limit, the argument, but I don't want to write that two different times. So I'm just going to show you that like the derivative itself exists. That's what differentiable means. Now, if we want to take the derivative of a function, we don't always have to use this definition. That's where we get a bunch of rules and properties and like given functions that we should pretty much memorize. The first one is when you take the derivative of a constant, it's 0. Derivative of x to the power of n, this is called the power rule because it's a power, is equal to n times x to the power of n minus 1. So you basically take down the exponent and you reduce the exponent by 1. The sum rule is, sum and difference rule is when you add or subtract functions, you just do f prime of x plus or minus g prime of x. So you add or subtract their derivatives. Constant multiple, as you might expect, c of f of x, c times f of x is equal to c times f prime of x. Product rule, this is where we get into some of the other rules that aren't as common as these four, and you actually have to kind of derive, or you can derive them using the definition. It's not easy, but it's sometimes it helps with explaining it. So this one's when you take the product, it's not obvious what it's going to be. It's not just f prime of x times g prime of x. No, that is a common misconception. Instead, it's f prime of x times g of x plus f of x times g prime of x. It's a bit weird, but you should probably memorize that. And then ddx of a quotient f of x over g of x is equal to, again, not obvious, it's f prime of x times g of x minus f of x times g prime of x over g of x squared. So yeah, that's the product rule, that's the quotient rule there. In addition to this, you probably need to know the derivatives of some common functions. So derivative of e of x is equal to itself, e to the power of x. Derivative of ln of x is equal to 1 over x. Derivative of sine of x is equal to cosine of x. And derivative of cosine of x is equal to negative sine of x. That negative sign there is key. Okay. There's also a few more trigonometric functions you might want to know. So derivative of tangent of x is equal to secant squared of x. Derivative of secant of cotangent of x first is equal to negative cosecant squared of x. So you see kind of a pattern. It's just going to be the negative, and then you take the cofunction of whatever function. So if this was cosine, the cofunction of cosine is sine, and so you just take negative of that. And then the last few we have, I'm running out of space, ddx of secant of x is equal to secant of x times tan of x. And if you notice the pattern, cosecant of x is negative cosecant of x times cotangent of x. And so those are the most common derivatives you should know for this unit. And that's actually it for this unit. It was it was very short, this unit. Next unit is continuing on derivatives. A lot, like the first few units all focus on derivatives. We have a lot of derivative related units. This one is differentiation. I'm not going to write the entire title. Is just going to call other functions. Officially it's composite, implicit, and inverse functions. So we're going to learn all of that in this unit. The first thing is the chain rule. It's another important rule that's usually taught a little while ago before you talk about like derivatives of certain function, but in the AP curriculum it's in this unit. So basically if there's f of g of x, the derivative of that is that's a composite function. It's just equal to f prime of g of x times g prime of x. And this is probably best illustrated with an example. So if you have something like square root of sine of x, or actually no, let's make it a bit simpler so that you can see exactly where the functions are. So if it's x squared, sine of x squared, that means g of x equals sine of x, and f of x equals x squared. And so the derivative would just be f prime of g of x. So f prime of x is 2x, because you bring down the 2 and reduce the exponent by 1. So it becomes 2 times sine of x, because you replace g of x into f prime of x, times g prime of x. Well, derivative of sine is cosine. So 2 sine x cosine x is the derivative of sine squared x. Okay. Then we've got implicit differentiation, which is basically you don't have y equals a certain function like you do with other functions. Instead, x and y are both related to each other through an equation like y cubed plus x cubed plus x times y equals 5. And if you want to take the derivative of this with respect to x, like dy dx, you just take the derivative of the entire equation. And that's what implicit differentiation is. Every time you see a y, you have to multiply it by dy dx because of the chain rule, because y is a function of x. And so this becomes y cubed is 3y squared times dy dx, plus derivative of x cubed is 3x squared. No dy dx because you're not taking the derivative of y. And then x times y, that's product rule. So if you do f prime of x times g of x, so derivative of x is 1 times y is just y. And then derivative of y is just dy dx. It's 1 times dy dx, and x just stays itself. So it's x times dy dx equals derivative of any constant is 0. And so you can just factor out the dy dx and move the other stuff to the other side. So if you take out the dy dx, it's dy dx times 3y squared plus x is equal to negative 3x squared plus y, because you just move these two to the other side. And we divide, we get dy dx by the way, there should be parentheses here, is equal to negative of 3x squared plus y over 3y squared plus x. So yeah, implicit differentiation is one of those that really you need an example to actually figure out how to do it. We can use implicit differentiation to figure out what the derivative of an inverse function is. So if you have f of x and its inverse f inverse of x, that means that the value of f inverse prime of x, so the derivative of the inverse function at a certain value of x, is equal to 1 over f prime of f inverse of x. So that's pretty much a rule you should know. So if it's like x squared and root x, which are simple to find the derivative of, you just say, well, what if x equals 4? The derivative of root x at x equals 4. So you do 1 over f prime. Well, f prime is 2x. And you plug in root of 4 is 2 into that, so it becomes 1/4 is your answer. And then you can use implicit differentiation again to find the derivatives of some inverse trig functions. So derivative of inverse sine of x is equal to 1 over root 1 minus x squared. I'm not going to show you how to do it, but it just involves right triangles and trigonometry, as you probably expected. And implicit differentiation, of course. For inverse cosine, it's just going to be negative of the same thing, so negative 1 over root 1 minus x squared. For inverse tangent of x, it's equal to 1 over 1 plus x squared. Inverse cotangent of x is equal to negative of that. And then we got secant of x, inverse secant of x. That's equal to 1 over x times square root of x squared minus 1. And there's usually an absolute value around the x because you want to restrict it to positive values only. And as you might imagine, cosecant of x, inverse cosecant of x equals negative 1 over absolute value of x times square root of x squared minus 1. So yeah, that's that. And the last thing in this unit is higher order derivatives. So we've just been dealing with derivatives. So first order derivative, y prime. You can also get y double prime, y triple prime. It's just you keep on adding primes to it. Once you get to 4, though, it's usually written as y and then like 4 in parentheses, not to be confused with exponents. And so you can go all the way to yn, which is the nth derivative of a function. When you're writing in the other notation, so like dy dx, it becomes d squared y over dx squared. So this squared goes before the y in the numerator and after the x in the denominator if you want a higher order. So it's d to the n of y over dx to the n. So yeah, that's that. And that's the end of this unit. 3 units done so far, 7 more to go. The next unit is contextual applications of differentiation. So this is half of the applications of derivatives. The next unit is the other half. Oops. Yeah, so that's why these differentiation or derivative units are short, but there are also a lot of them. So straight line motion is the main application we're going to cover. It's just where you have position x of t. You got velocity, or s of t, or y of t, whatever. You got velocity, which is v of t, and you got acceleration, which is a of t. The derivative of x of t, or position, is velocity, and derivative of velocity is acceleration. So that's pretty much all there is to this application. It means that the second derivative of position, second derivative of position is equal to acceleration. Yeah. Okay, moving on to something a little more complicated, related rates. So that's when there are multiple different rates, there are multiple different quantities that are all changing in relation to another. And there's an entire process you can do, but I feel like the best way to explain is an example. So, very simple example. You got a right triangle. The horizontal leg of a right triangle is increasing at a rate of 3 feet per second. Vertical is decreasing at 2 feet per second. At the instant when the horizontal leg is 7 feet and the vertical leg is 1 foot, what is the rate at which the length of the hypotenuse is changing? Is it increasing or decreasing? All right, so let's see. So if we write this as x, y, and z, we know that x squared plus y squared equals z squared. That's just the Pythagorean theorem. We also know that in this moment, x equals 7, y equals 1, dx dt is equal to 3 feet per second, and dy dt is equal to negative 2 feet per second. And we want to find dz dt. So we also know technically what z is just by plugging it into the Pythagorean theorem. So it's equal to square root of 1 squared plus 7 squared, or square root of 1 plus 49, which is square root of 50, or 5 root 2. So z is 5 root 2. All right. So what can we do? We can use implicit differentiation and just take the derivative with respect to time of both sides, giving us here 2x times dx dt, because remember chain rule, x is a function of time, plus 2y times dy dt is equal to 2z times dz dt. We can actually cancel off the 2 everywhere. Oops. Okay. And we can plug in everything we know. X is 7, dx dt is 3, plus 1 times negative 2 is equal to 5 root 2 times dz dt. And this becomes 21 minus 2 is equal to that. And so 19 over 5 root 2 is equal to dz dt. And since that's positive, it means it must be increasing as time increases. Next application is linearization, which is basically finding the best linear approximation to a function. And that's just using the tangent line. So if you have a function f of x, you can find the derivative at that value, so f prime of x. And you find the slope of the tangent line at a, so f prime of a. And so since the function passes through the point a comma f of a, the tangent line would be y minus f of a is equal to f prime of a, the slope, times x minus a. And you just use this equation of a line to approximate it. So if you have a function like that, and a is right here, the tangent line would be something like that. And so you use that to approximate what the next value of the function would be at a different time. So it's pretty inaccurate, and we're going to learn about a lot of other methods to approximate values of a function later on, starting with Euler's method in, I think, Unit 7, and then Taylor polynomials in all the way in Unit 10. So this is just the first of a few different methods. Oops. We still have actually one more application, which is L'Hopital's rule, and that's finding the value of an indeterminate limit. I didn't really mention this earlier, but if you have a limit that goes to 0 over 0 and infinity over infinity, it's called indeterminate, which means you just can't plug it in and expect it to work. Kind of like that sine x over x we saw before. And so what L'Hopital's rule is saying is that if you have an indeterminate limit, the limit as x approaches a of f of x over g of x is equal to limit of as x approaches a of f prime of x over g prime of x. So you don't take the derivative of the quotient f of x over g of x, you just take it of the numerator separately and the denominator separately, and then take the new limit to see if that works. If it doesn't work, you do L'Hopital's again and again until you do get a non-zero, non-indeterminate value. Okay. Yeah, that's pretty much it for this unit. Moving on to Unit 5, which is analytical applications of differentiation. So this is where we get into curve sketching, which is one of the main applications of differentiation, and then we get some other applications as well. So before we start with curve sketching, the mean value theorem, MVT usually, basically says that if it's continuous on AB, differentiable on AB, on AB, this is closed, meaning inclusive, exclusive, because it's open. Then there's at least one point between A and B, such that the instantaneous rate of change of the function is equal to the average rate of change. Basically saying you got a function like that, the average rate of change is just the secant line going through both points. There's got to be at least one value, one point on the interval such that the derivative at that point is equal to the average rate of change. In other words, f prime of c is equal to f of b minus f of a over b minus a. Okay. Then moving on to curve sketching. Curve sketching is basically using the values of derivatives and second derivatives to figure out how a graph looks like the graph of a function. So the first derivative, f prime of x, tells us about increasing, decreasing. And critical points. Critical points are basically points where the first derivative is equal to 0. And so if it's equal to 0, then in most cases it'll be either changing from increasing to decreasing or decreasing to increasing. And you use the first derivative test to figure that out, which basically says if f prime is greater than 0 on some interval, then it's and f prime is less than 0 to the right. So let's say you got a function like this, or how do I want to explain? Okay, so to the left of a certain critical point, f it's a positive derivative, and to the right it's a negative derivative. And that means the critical point was a maximum, because when f prime is greater than 0, that means it's increasing. When it's less than 0, it means it's decreasing. And so that means it had to have been a maximum at that point. If f prime of x is less than 0 to the left and greater than 0 to the right, then it's a minimum. If it's any other combination, like greater than 0 on both sides, less than 0 on both sides, then it's not a local extrema. It's not like a maximum or a minimum. It's just a random critical point. These are all local extrema, local maximums and local minimums. If you want to look at absolute maximums and minimums over a certain interval AB, you just look at all of the critical points over AB and also the endpoints A and B specifically, because it could be a function that looks like this, where there are no critical points, but then like A is the maximum, B is the minimum. So you also have to consider the endpoints. So you look at every single critical point and the endpoints of the function, and you see which one has the largest value. You just plug it into the function, see which one has the largest, which one has the smallest, and you get the absolute extrema. The second derivative tells us about concavity, basically concave up, concave down. Concave up is basically like an upwards facing parabola, concave down is a downwards facing parabola. That's the simplest explanation I can give. Inflection point is where it changes from concave up to concave down, or vice versa, also known as point of inflection. If the second derivative is equal to 0, then it's a point of inflection. If it's greater than 0, that means it's concave up. If it's less than 0, it means it's concave down. And so what the second derivative test says is that if you have a critical point you found using the first derivative and setting it equal to 0, if f prime at that value is greater than 0, then it's a minimum. If f prime double prime is less than 0, then it's a maximum. Because if it's concave down and a critical point, that means it has to be a maximum. If it's concave up and a critical point, it has to be a minimum. And if it's equal to 0, then it's inconclusive. It could be, you have to do some more tests on it. The next application is optimization. Optimization is kind of like related rates in the sense that it's like word problems, and the best way to actually do it is to do an example. And so let's see the example. You got a cylinder. Volume is 5 feet cubed. And find the dimensions that will minimize the amount of material used. So optimization problems are always, you want to minimize something, you want to maximize something, and you have this other constraint. Like in this case, the volume is 5 feet cubed. So find the dimensions or whatever that will let us minimize or maximize whatever we want. So if this is radius and height are the two dimensions we care about. The surface area is what we want to optimize. And the formula for the surface area of a cylinder is 2 pi r squared plus 2 pi rh. And the volume of a cylinder is pi r squared h. And so we have the constraint pi r squared h equals 5. And we can solve for h by dividing both sides by pi r squared. So 5 over pi r squared is h. Now we can use the surface area formula and get a surface area equals 2 pi r squared plus 2 pi r h. Well, that becomes 2 pi r times 5, not s, 5 over pi r squared. Pi's cancel, one of the r's cancel, so surface area is 2 pi r squared plus 2 times 5 is 10, so 10 over r. And now we can take the derivative implicit differentiation of this with respect to r. And we want the maximum value of the surface area, so we're basically checking for a critical point and making sure it's the maximum. Since surface area is going to be like a constant, because we're looking for the maximum surface area, it's going to be equal to 0. And then bring down the 2, so it becomes 4 pi r plus, and then derivative of 1 over r is equal to 1 over r squared, negative 1 over r squared. And so this becomes minus 10 over r squared. And that's equal to 0. So you solve for r. I'm not going to go through the algebra here because this is the calculus course and we don't have that much time. So r is going to be the cube root of 5 over 2 pi. And so that's going to be the maximum value of the value of r that gives us the minimum surface area. And then you just plug it in to find out what the height is, which you can do later. And then you can also plug it in to make sure that it is actually the minimum surface area. But for now, this is pretty much how you solve the problem. Last thing in this unit is implicitly defined curves. You can do everything we mentioned in this unit with implicit functions or implicit relations. So you can do curve sketching even if you're given an implicit relation like x squared plus 2xy equals 0. You can find the derivative, find where it's increasing, decreasing, concave up, concave down, etc. That's it for this unit, unit 5. So we're pretty much halfway done, but the last few units are definitely longer than these ones. That also marks us the start of integrals. So we're going to be starting to talk about integrals now. So unit 6 is integration. And accumulation of change. Okay, so starting with Riemann sums, which you probably learned about in pre-calc. A Riemann sum is just the sum of like shapes that give us the area under a curve. So you got something like this, you can just use rectangles or trapezoids or whatever to estimate the area under the curve. The formula for a left Riemann sum, or left endpoint Riemann sum, I equals 0 to n minus 1 of f of xi times delta x. Right Riemann sum is the same thing, but I equals 1 to n instead. And so you can use either of these two. There's also midpoint, but I'm not going to go over it. This is just a brief review. Basically, what we're saying is you can use Riemann sums to approximate it by just coming up with n different rectangles underneath it. But if you take the limit as n approaches infinity of this Riemann sum, whichever one, it doesn't matter, whichever one you prefer, they both give you the same result. That is going to be the exact value of the area under the curve. And we shortened that form by just writing the integral from a to b of f of x dx. It's called the definite integral because it has these bounds that you have to calculate. There's some properties of the definite integral, namely that the integral from a to b of a constant function is equal to c times b minus a. So you just take the difference and multiply it by that constant. The integral from a to b of a constant times a function is just you take the constant out. And don't forget this dx, that's always important. Every time you have any type of integral. From a to a of f of x, dx is 0 because you're integrating like a single point, not over an interval. Integral from a to b of the sum or difference of two functions, you just split it up, a, b, f of x plus or minus dx. Plus or minus integral of a, b, g of x dx. Integral from b to a of f of x dx is equal to negative integral of a to b of f of x dx. And then last one, integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral of c to b f of x dx. So basically, if c is a point between a and b, you can split it up into different intervals. Okay, we can relate this to derivatives using the fundamental theorem of calculus. The first part of the fundamental theorem says that if you take the derivative of an integral with a to x, not any other number b, because if the result of a definite integral is always going to be a number that you're under the curve. But if you have x as one of the bounds, or like a function of x as one of the bounds, you're going to get a function, not a number. And so f of t dt is equal to f of x. So basically saying that derivatives and definite integrals undo each other. And then antiderivatives is basically the opposite of a derivative. If f prime of x equals g of x, then f is an antiderivative of g. And we represent it with integral of g of x dx is equal to f of x. This is an indefinite integral because you don't have the bounds. And so the second fundamental theorem, or the second part of the fundamental theorem of calculus, basically says that integral from a to b of f of x dx is equal to f of b minus f of a, where f of x is the antiderivative of another function, f of x. Pretty confusing, but if this is the function in the argument of the integral, and you find the antiderivative of it, you can just plug in the values a and b into the antiderivative and subtract them. Another thing is that always when you take the antiderivative of a function, you're going to end up with a plus c. So this plus c, because whenever you take the derivative of a constant, it becomes 0. So you never know if the original function ever had a derivative, had a constant term before you took the derivative, and so you always add that constant c back. Some of the basic rules of antiderivatives, kind of like, you just take the opposite of the rules of derivatives. So if it's x to the power of n, the integral of that is 1 over n plus 1 times x to the power of n plus 1 plus c. For e to the x, it's still e to the x. For 1 over x, it becomes ln absolute value of x, and so on. If you ever see a derivative rule, you can swap it around and get an antiderivative rule. So I'm not going to go over those very much. I'm going to erase the board, and we're still not done with this unit, though, because it's a pretty long unit. We're going to be talking about the techniques of integration now. So you can calculate an antiderivative using u substitution, also known as changing the variables. So basically, an example of it is if you go from let's see, sine of x over square root of cosine of x dx. You can set a new function u equal to one of the functions there, so cosine of x. Then you take the derivative of that, which gives us negative sine of x dx. And you make sure that the other function in the integral is there. So we see a sine of x dx here. We want sine of x dx. What is that equal to in terms of u? It's just equal to negative du, because you negate both sides. And so you can rewrite this as integral of negative du, because that's what sine of x dx is, over square root of cosine x. Well, cosine x is u. So now you wrote this entire integral into negative 1 over u du, all in one variable, and it's pretty simple to evaluate, because it's just negative u to the power of negative 1/2 du. And we know that integral of x to the power of n dx is equal to 1 over n plus 1, x to the power of n plus 1 plus c. The negative goes outside, so it becomes negative 1 over 1, negative half plus 1 is positive half, and 1 over a half is 2. So it becomes negative 2 over, negative 2. And then it becomes x to the power of negative 1/2 plus 1, which is 1/2. So negative 2 root x is plus c. And remember, it's u, not x. And then we just plug in u equals cosine of x back into this. So the result is negative 2 root cosine of x plus c is your antiderivative. Okay. There's also integration by parts, which is just integral of u times dv is equal to u times v minus integral of v times du. Pretty complicated, but example, integral of x times e to the x dx. Well, that's going to be hard to evaluate because we don't know anything. To do that, even if we use substitution like u equals x, that's not going to help us a lot. And so what we do is we say u is equal to, in this case, we can say u is equal to x. That means the derivative of that is just dx. And we said the other function, e to the power of x dx, as dv. Not v, but dv. And then we take the antiderivative of that. That's pretty simple. We know that's just e to the x. We ignore the plus c for now. And the way I like to remember it is now it becomes a 7. It's just a 7, and this little cross in the middle shows you helps you remember it's minus. So first it's x times e to the x, u times v, minus v times du, integral of e to the x times dx. And that we know is e to the x. So it just becomes x e to the x minus e to the x plus c. Now we remember the plus c. And that's the antiderivative. You just need practice with this. Keep doing practice and you'll get it. You can use long division if you have a integral like integral of x cubed plus x over x minus 1 dx. Looks complicated, but if you use long division, it's just going to become integral of x squared plus 2 over x minus 1 dx, all of which we know how to integrate. So you can just do it that way. Then we got partial fraction decomposition, which is turning a fraction into the sum of two other fractions. So if you have something like x plus 9 over x squared minus 3x minus 10, you can factor the denominator to be x minus 5 times x plus 2, and x plus 9 in the numerator. And then what you basically do is, well, you can separate into a over x minus 5 plus b over x plus 2. And you basically do a system of equations to solve for what a and b are. So you do a times x plus 2 plus b times x minus 5 gives us x plus 9. And then you solve for a and b. In this case, it's going to be 2 and negative 1. But yeah, that's pretty simple there. And then last topic for this unit is improper integrals, which is basically an integral that includes infinity as one of the bounds of integration. So if like 0 to infinity of 1 over x squared dx. Another common example is e to the negative x dx, which looks something like that. And so the way to evaluate it is let it become limit of a approaches infinity of integral of 0 to a of e to the negative x dx. And then evaluate this and then plug in back a approaches infinity. So in this case, integral of e to the negative x is just negative e to the negative x plus c, but since it's a definite integral, we can evaluate it from a to 0, which is negative e to the negative a plus e to the negative 0. E to the negative 0 is just e to the 0 or 1. And then e to the negative e to the negative a, and you do limit as a approaches infinity of that, and e to the negative infinity is 0, so that just becomes 0. So your answer is just 1. The answer to that improper integral is 1. Not all improper integrals converge to a number like this. They can also diverge, but you just have to test it to see if it diverges or not. Okay, Unit 7. We're moving pretty quickly, but again, these last few units are killer. They're quite confusing and quite long. Okay, this is an application of integrals and derivatives called differential equations, and that's just an equation that has a derivative in it. So, for example, d squared y over dx squared is equal to negative y. Also written as y double prime equals negative y. And there are a few ways to solve this that we're going to talk about in this unit. So first is slope fields, which is basically a visual representation of the slope at each point. And so you just plug in like x comma y of different values into the derivative. So I'm not going to use this as an example. I'm going to use a different example like y prime is equal to x plus y. So if you plug in like 0 comma 0 into there, 0 plus 0 is 0, so this would be perfectly flat. If you plug in 1 comma 1, 1 plus 1 is 2, so that'll be 2. If you plug in 1 comma 0, that would be 1 plus 0 is 1, so that would be 1 less slope. And then you just fill this out for the rest of the points on the graph. And you just keep going, and then you'll have a kind of visual representation of it, and you can maybe draw in like how the graph should look like based on how it follows along those slope lines. Building upon this a little bit, we can use Euler's method, which is basically, like I said, another method for estimating the value of a function, similar to that linearization one we were talking about a few units ago. Euler's method uses the differential equation to actually calculate that derivative, and it uses different steps. So earlier we said, oh, you just take the line that that goes through the point at AB, or at A comma f of A, and it use the slope of the line at that point to get the entire equation and then plug in the new value. Instead, we're doing that like multiple times over. And so if we have something like this, where we don't know what the original function is, and so we can't just plug in the value into the original function, we have to get a line using the derivative, the slope, and then use that line to estimate the next step, and then keep on doing that. So instead of going from 0 straight to 0.5 like we did back in linearization, you go 0 to 0.1, then use the values in 0.1 to get a line that estimates 0.2, and so on and so forth. So using this as an example, you have at 0, let's say it starts at 0 comma 0. At 0, it's y minus 0 is equal to, let's just add a 1 here, is equal to 0 plus 0, 1 plus 1 times x minus 0, which is just equal to y is equal to x. Okay, and if you plug in 0.1, the next step into this, you get 0.1 comma 0.1 as the next point that you use to estimate. So now the new equation becomes y minus 0.1 is equal to the new slope, which is 0.1 plus 0.1 plus 1, or 1.2, times x minus 0.1. And this becomes y minus 0.1 equals 1.2x minus 0.12, adding 0.1 to both sides. Y is equal to 1.2x plus 0.88, and you keep on doing this. Now you plug in x equals 0.2 into this and get 0.2 comma the next value, and you just make the new line for that, and so on until you get into 0.5. So that's Euler's method. Okay, now how do you actually solve a differential equation? So let's go back to another example. Y prime is equal to x times y, let's say. The way to solve a differential equation like this is but using separation of variables. This equation is separable because you can move all the y's to one side and all the x's to the other. This is not separable because you can't move the y's to one side, and I'll show you why in a second. You can write y prime as dy over dx is equal to x times y. So you divide both sides by y and get 1 over y times dy dx is equal to x. But we still have this x here, so you just multiply both sides by dx and get 1 over y times dy is equal to x dx. The reason we want that now is because we can just take the integral of both sides, and we have the dy here, we have the dx here, and you solve it that way. Integral of 1 over y is ln absolute value of y, and that's equal to integral of x, which is 1/2 x squared, and you just take e to the power of both sides, so it becomes y is equal to e to the power of 1/2 x squared. And so that's basically how you solve, and you're always going to want to have a plus c. Since there's two integrals, it'll be plus c1 and plus c2, one on each side, but you can just combine them to form one constant c. So this becomes plus c. Using properties of exponents, you can just move that into e to the power of c, which itself is a constant, and so you can just multiply the entire exponential function by a c in the front. And so that's going to be your solution to the differential equation. Something like this, dy dx is equal to x plus y. Let's just use that for simplicity's sake. By subtracting y from both sides, you're going to get negative y plus dy dx equals x. There's no way to multiply both sides by dx, because then you'll also get a negative y dx, because that's also getting multiplied. And so it's not separable in that. You cannot separate into y's and x's on both sides. Okay, there's basically one or two more topics in this unit, focusing on different models, starting with the exponential model, which is represented by y is equal to a times e to the power of kt, and the differential equation for that is dy dt is equal to ky. That, if you were to solve this using separation of variables, you would get the exponential function as a result. And so a lot of word problems rely on the exponential model to solve for k, solve for a, giving you different stuff. And so you just solve it like that. The new type of model is the logistic model, which there is no clean equation to really write. There is an equation. It's not very nice. You probably shouldn't memorize it. Instead, you just know the dy dt is equal to ky times m minus y. So you're just multiplying by m minus y, and that's the m is the carrying capacity. So now it kind of levels off. The graph of a logistic equation looks something like that, where it starts to grow. It grows very rapidly, and then it flattens out after a while. And so yeah, there's also a lot of word problems about logistic models, and you basically solve this differential equation. This can easily be separated, and you would probably use partial fraction decomposition or something to solve it. And yeah, that's pretty much logistic models, and that's it for differential equations as well. All right, Unit 8. Unit 8 is applications of integration, all condensed into one unit. So it's pretty heavy, but there aren't as many applications as the derivatives unit. First one, again, is position, velocity, acceleration. We said x of t, y of v of t, and a of t. They're all derivatives of one another. This is the derivative. Velocity is derivative of position. Acceleration is derivative of velocity. If you go the other way, velocity is the integral of acceleration, and position is the integral of velocity. So there's that application there. Then there's also the average value. So the average value of a function is equal to 1 over b minus a times the integral from a to b of f of x dx. So you have a function like this that looks something like that. The average value would be something like this, and the way you calculate that would be using this formula. You have a set interval from a to b, and you plug it into this formula, and you're going to get an average value of that function. There's also going to be a lot of word problems that rely on the accumulation part of integrals. That's why the entire unit was called integrals and the accumulation of change. Yeah, and so an example problem would be something like a quantity that's changing over time. So like a tank of water that contains some amount of water, and then we're given a function that that models the rate of change of that of the water, and we just use the integrals to actually find out how many disappeared. So if you say that the tank leaks at a function of 3 times absolute value of sine of t, for example, you would take the integral of that to find out actually how many gallons of water leak. This is just the rate of change of leakage, how fast the water leaks. You take the integral to find out how much water actually leaked, and then use that to answer whatever the question they're asking you. Some other applications of integrals. The area between two curves is literally just an integral. If you have a curve f of x and g of x, the area between them over their intersection points a and b is just going to be integral from a to b of the top function, in this case g of x, minus the bottom function f of x dx. You just solve it, and you're going to get the area between them. You can also use horizontal rectangles. That's another application, which I'm not going to go too deep into. Is just using dy and making all the function in terms of y instead of x, and changing the bounds and everything, obviously. And yeah, that's going to give you different results. I mean, that's going to give you the same results with a different method. So it just depends on whichever one's easier. Then you can also find volumes using integrals. And there's a few different types. First one is volumes with cross sections. And so that's taking like the function, and then you take the area of it, and you're basically using that area and cross section. So let's say like you know that a cross section of a square is there at every point in this. So using a different color probably would help. So a square is there at every like line of this, and so you would get like a 3D shape pretty much. What the formula for this is, you just take the integral of the function, so you find the area under it, and in this case it's just going to be dx, a to b. That's just going to be the area, but then you would multiply that by the cross section. In instead of just doing f of x, you would like square it to get the area of a square. So since in this case it's squares, it would become f of x squared. Instead of just f of x, it's f of x squared, because f of x is one side of the square, and then the area of a square is just the side squared. If it was something like a semicircle, you would do 1/2 pi radius squared. In this case, the value of the function would be the diameter, so it would be diameter over 2 squared, and so you would plug that in. Instead of diameter, you would put the function f of x over 2 squared, and so on. Okay, that's one way of finding volume. Another way is called solids of revolution. So you can basically revolve solids across different axes and get like a revolution, get like a solid or like a 3D shape that you can find the volume of. So the first method is the washer method. I'm basically saying that if the rectangles you're taking off, in this case dx, if that's perpendicular to the axis of revolution, you use the washer method, and that's just rotating the function as a whole around an axis. And the formula for that pretty much is the volume is pi times a to b of r squared dx, where a and b are the bounds and r is the function as a whole, so it just becomes a times b times f of x squared dx. Washer like refers to an area between curves that's revolved. And so you get kind of like a donut kind of shape. It's hard to visualize on a 2D surface like a video. But in that case, you do g of x squared minus f of x squared. So it's just like taking the larger area minus the smaller area. It's not g minus f squared, it's g squared minus f squared. So be careful with that. You can also do cylindrical shells, which is when the rectangles are parallel to the axes. So if you have something like this, just like before, but the axis is here, you would use cylindrical shells, and you would get something like that. And the formula for that is 2 pi times the integral of a to b of f of x dx. So f of x in this case is the function, and that's the radius away from the axis of revolution, and 2 pi gives us the circumference of the circle. So it's just like, that's why it's called cylindrical shell. It's a thin-walled cylinder, and you're just finding the volume of that, because 2 pi r gives us the volume of the cylinder. Then you also have to multiply by the radius itself, x, because instead of 2 pi f of x, my bad, the original form is 2 pi integral ab of x dx, because x is the radius away from the axis, not f of x, and that gives us the circumference of the circle. Then you multiply that by f of x, because that's the height of the circle, of the circle or of the cylinder you're looking at that snapshot in time. And so it becomes 2 pi x f of x as the volume of a thin-walled cylinder, and you just repeat that over and over again for every point from a to b. So that's that. And then last application of integrals here is arc length. So if you're given a function and you want to find out how long it is, or like the distance traveled along that path, the formula is integral of a to b of square root of 1 plus f prime of x squared dx. So that's going to be pretty hard to calculate unless it's a very simple function. So yeah, that's just the formula though. You plug in, you take the derivative of the function you're looking for, you square that, add 1 square root of that, integral from a to b, and that's going to give you the arc length. You're probably going to have to use a calculator to actually calculate it, but that's the formula. That's it for this unit. 2 more units left. Probably the hardest 2 units of the course, but you know. This next one is parametric equations, polar coordinates, and vector valued functions. Again, I'm not writing everything out. I'm just writing the basic keywords. Okay, starting with parametric equations, you should know what all of these are. Parametric equations are using another variable t, or whatever other variable, In this case, x of t and y of t are the two functions that describe the curve. And so you just do similar stuff. So x dt is what you get if you do x prime dy dt, but you mostly want to do dy dx, and so that's just y prime of t over x prime of t, because the dt's cancel. If you want to take the second derivative, it's a lot more complicated, but that's just the ddt of y prime of x, which is this right here. So this, you plug that in, and you take the derivative with respect to time over dx dt, or x prime of t. So yeah, don't memorize these formulas, just try to reason it through, or yeah, it should be pretty simple once you actually do a problem like it, but for now, I wouldn't suggest memorizing these formulas. You can also find the length of a parametric curve. It's similar to the arc length formula we just saw, but in this case, instead of 1 plus the derivative squared, it's x prime of t squared plus y prime of t squared dt. Think of it just as Pythagorean theorem. When you're moving along a curve, you have this small Pythagorean theorem, and you're just iterating over that multiple times. That's parametric equations. For vector valued functions, it's very similar, except it's vector x of t comma y of t, and that gives you like a position vector, and you can find the velocity vector is just the derivative of that, so x prime of t, y prime of t, and acceleration is, you know, you can reason out, it's just derivative of velocity. Now, what's interesting is this arc length formula is now going to give you pretty much the distance traveled by an object that moves with these position values. So vector value functions, parametric equations are the same thing, but vector valued is in terms of usually position, velocity, acceleration. Parametric can pretty much be anything. And so this arc length formula is literally just the distance traveled on that path. And so it's just the square root of the speeds, the x and y components of the speeds. And then last thing of this unit is polar coordinates, which is, again, you should probably know, is just x is equal to r cosine theta, y is equal to r sine theta. R squared is equal to x squared plus y squared, and tan of theta is equal to y over x. These are the four main equations that govern polar coordinates. It has these circular coordinates, and you got like functions in them, like that, different colors, like that. And you can find the slope of the line tangent to the polar curve, similar to parametric equations, where it's dy d theta over dx d theta. Basically write y and x in terms of theta, because usually you're given r in terms of theta, and then you just plug in r into this equation, these two equations, to find x and y, and then take the derivatives, divide them, and you're going to get dy dx, the slope of the tangent line. You can also find the area bounded by the polar curve. This one's a lot more confusing, and I would definitely suggest a lot of practice with them, but it's integral from a to b of 1/2 r2 squared minus r1 squared. Or sorry, that's if you have multiple curves, but in general it's just r squared d theta. Like I said, in multiple curves, it becomes r2 squared minus r1 squared. Kind of like the washer method, but different. A and b here are angles, so if you're going from like this angle to that angle, you would use this formula. That's it for this unit. Last unit of calculus is infinite sequences and series. Okay, so a sequence, you probably know. Series, you probably know. Series is just the sum of terms in a sequence. An infinite sequence just goes on to infinity, and an infinite sequence converges if limit as n approaches infinity of the sequence, of the terms in the sequence, actually goes to like a non-infinity value, like a finite value, and diverges if it goes all the way to infinity. So something like 1, 2, 4, 8, 16 geometric sequence diverges because it goes all the way to infinity, but 1, 1/2, 1/4, 1/8, that converges because it goes to 0. So yeah. Now, an infinite series is the sum of all these terms, and those don't converge to diverge, kind of like what we just said. Instead, the sum of an infinite series itself is just the sum AFN from n equals 0 to infinity, which is just a0 plus a1 plus dot 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 all the way to infinity. If you just do it to the first n terms, like capital N terms, plus a of n, it becomes a partial sum s of n. And if you take a sequence of these partial sums and see if that converges. If that converges, then the infinite series itself converges. That's the definition of the convergence of an infinite series. All right. There's a bunch of different tests you can use to see if a function converges. I'm just going to speed through them really quickly. First is the nth term test. If the nth, if limit as n approaches infinity of the sequence is not equal to 0, then the series diverges. Pretty simple. It doesn't tell you if it guarantees convergence, but it eliminates a lot of different functions, because it's like there's no way that converges. But for some other functions like 1 over x, you're not sure if it converges. It passes the nth term test, but that's not guaranteed convergence. Nth term is just to violate some, or to get rid of some values. Second test is the geometric series test. Basically, if absolute value of r is less than 1 in a geometric series, then it converges. If it's not, then it diverges. Third is p-series. P-series is just in the form sum of 1 over n to the power of p. And if p is greater than 1, it converges. If it's less than or equal to 1, it diverges. Okay. Then we got the integral test. Basically, a series that's in the form a of n, where a of n is equal to f of n, a function. It converges if and only if the improper integral from 0 to infinity f of x dx converges. So you basically turn the infinite series into an improper integral and see if that converges or not. Then we got the direct comparison test. And if you have a series that you know that converges or diverges, then if a of n is less than or equal to b of n, and b of n definitely converges, then a of n also converges. So for every term n, if one series is definitely smaller than the other, like in a graph, if it looks like that, and this converges, then you know that also converges. That's a bad example. That wouldn't converge. If it's something like this, if you know this converges, then this also converges. On the other hand, if you know that this diverges, then you know that the other function that's greater than it also diverges. Then we got the limit comparison test, which is similar, except you take the limit as n approaches infinity of a of n over b of n. If this is positive and finite, so not 0, if it's L where L is positive and finite, then either both of them converge or both of them diverge. So if you know one of them converges and you want to look at the other one, you take the limit, and if it's positive and finite, then you know that one of them, the other one also converges. Same thing with diverges. Seventh test is the alternating series test. This only works for alternating series where it's negative 1 to the power of n of a of n. So if it's something like 1 minus 1/2 plus 1/4 and so on, if it alternates the sign, then if a of n is decreasing and limit as n approaches infinity of a of n is equal to 0, then the series converges. Remember, it has to be both decreasing and the limit has to go to 0, then the series converges. And the last test is the ratio test, in which limit as n approaches infinity of the absolute value of a n plus 1 over a n. So the next term over the current term, if that's equal to L, if L is less than 1, then it converges. So you want L to be less than 1. If it's greater than 1, it diverges. If it's 1, it doesn't mean anything. It just means that it's inconclusive. So you need to use a different test. The ratio test doesn't work for that specific example. Okay, so that's convergence and divergence of series. a few other topics in that. So additional, so there's two types of convergence. One is absolute convergence and the other is conditional convergence. So if you have a series AN, if absolute value of AN converges, then it's absolutely convergent. Pretty easy to remember. And if a series is absolutely convergent, that means it's convergent as a whole. That means that this also converges if this definitely converges. On the other hand, if AFN converges, but the absolute value doesn't, then it's conditionally convergent. That actually does happen for a few functions. For example, -1 to the power of n times 1 over n. That is conditionally convergent because it passes the alternating series test, number 7, where it is a decreasing function, and the limit as n approaches infinity of 1 over n is 0. But if you take the absolute value and just get 1 over n, it fails the p-series test. So it doesn't absolutely converge, it conditionally converges. Of course, it can also just diverge as a whole if it doesn't conditionally converge either. Okay, moving on to power series. Power series include an x term. So, for example, something like n equals 0 to infinity of AFN, like a normal sequence, times x minus c to the power of n. That's an example of a power series. It's centered at a value c, and you can use the ratio test mainly to see if it converges or not. And all of these do converge usually, except the point is where do they converge? And so you need to find the radius or interval of convergence, where you do the ratio test and you get an equation like absolute value of x is less than 3. That means that the radius of convergence has to be 3. So, or absolute value of x minus 2 is less than 3. That means the radius of convergence is 3, and the interval is going to be from -1 to 5, because the center is at 2. It's centered at 2, and the radius is 3. So it's from -1 to 5, for example. This comes from the ratio test because there's that absolute value, and you want to make sure it's a positive finite value. So you just say this is, or sorry, not positive finite. This has to be less than 1. So you just use that absolute value inequality, and you eventually get something that looks like this. Now, you don't know if these are open and closed brackets yet. Instead, you actually have to plug in x equals -1 and x equals 5 into the power series and see if that converges or not. So if it does converge, you put an open, you put a bracket. If it diverges, you put parentheses. All right. Some specific types of power series are Taylor polynomials and Maclaurin polynomials. Taylor series and Maclaurin series. But if we go back to the polynomial part of it, that's just going to be a limited version of this series. These series are power series that approximate a certain function. And so there's a few of them you probably need to memorize. 1 over 1 minus x, for example, is given by the Taylor series n to 0 to infinity of x to the power of n. So you should probably memorize that one. This, if you expand it, is just 1 plus x squared plus dot dot dot. ln of 1 plus x is the power series. In this case, from 1 to infinity, not 0. So that's the weird one. Pay attention to that. Is the alternating series -1 to the power of n plus 1 times x to the power of n over n. I'm going to erase all this over here so we have some more space. For sine of x, it's again from n equals 0 to infinity of -1 to the power of n times x to the power of 2n plus 1 over 2n plus 1 factorial. Cosine of x is, again, same thing. But in this case, it's just x to the power of 2n over 2n factorial. And then finally, e to the x is equal to sum from n equals 0 to infinity of x to the n over n factorial. Similar to this ln one, except n factorial in the denominator, not n. And it's also not alternating. These are all Maclaurin series because they're centered at 0. If they're centered at any other value, it's a Taylor series. So these 5 you should memorize, maybe a few more that your textbook has or whatever. What can you do with these, though? You can use Taylor polynomials, which I'm going to erase some more. 1 second. Taylor polynomials are just finite versions of these series where, like, the fourth order Taylor polynomial is just from 0 to 4. So it would be like the sum from n equals 0 to 4 of the Taylor polynomial, like x to the power of n, or Taylor series. And it's usually in the form a of n times x minus c to the power of n, like I said, where a of n is the nth derivative of the function at a value c, the center, over n factorial. And so the general formula for any Taylor polynomial of any a function is this. You take the nth derivative at that value divided by n factorial, you multiply it by x minus c to the power of n, and a few of them just so happen to condense down to these nice and easy ones you can memorize, and the ones that we use the most often. And so a lot of the times they can ask you a function like tan of x, and you just have to calculate it because you go n equals 0. Well, that's just the 0th derivative, that's tan itself. You evaluate tan of that value, you divide by 0 factorial, multiplied by x minus c to the power of 0, and so on. You just repeat that over and over again until it says, like, until n equals 3, n equals 4 or something. That's the type of problem you need to be worried about. And these Taylor polynomials are used to estimate values of the function, just like the Euler method, just like linearization. It's even more accurate than that. What is the accuracy? Well, that's where we get into error bounds. There's two types of error bounds you need to know for Taylor polynomials. One is the alternating series error bound, so that works for alternating series like these three, and a few more. And what is the value of it? Well, it's just equal to the magnitude of the next term that you're omitting. So if you're going from 0 to 4, for example, of this, then you would look at the next term and just calculate the value of that, and that's the maximum possible error that arises from your estimation. So as you might imagine, as you go on, the error decreases and decreases because each value in the Taylor series is smaller than the previous one. That's the alternating series error bound. There's also the Lagrange error bound, which is a lot more complicated. This works for alternating and non-alternating, but I would probably not use it for alternating series. You can just use an alternating series error bound for that. And so this just works for any Taylor polynomial. If you got an nth Taylor polynomial, m is the maximum value of the n plus first derivative on an interval from c to x. So if it's something like cosine of x, and n is 4, so you take the fifth derivative, and what is the maximum possible value on that interval? It's probably going to be something like 1, because the maximum value of cosine or sine of any sinusoidal is going to be 1. And so you just find that maximum possible value of that derivative, and then the error is equal to m times absolute value of x minus c to the power of n plus 1 over n plus 1 factorial. It's similar to just calculating the next term, but in this case, instead of just like calculating the value of the derivative at c, you're finding the maximum possible value of the derivative over an interval. So you just plug that in and you solve that error bound. That's actually it for this unit as well. And since it is our last unit, we are pretty much done with calculus. And so this was just a huge content review of calculus. Hopefully that helps. I know the test is tomorrow, so it's a bit late, but hopefully this helps, and good luck for your AP exam. See you next time.